Welcome, Mr. Sutton here with the Pre-Cal Honors 9-4 Part 2 Homework Solutions on Algebraic Limits of Piecewise Functions. For this problem, we're given this piecewise function with some log functions in it, and we want to know the limit as x approaches 2 for this function. Since 2 is a border value in this piecewise function between the first and the second rules, that means I have to look at the left and the right side limits as x approaches 2, and then compare those to see the two-sided limit. So my left-sided limit as x approaches 2, that's going to be this first rule, the before rule. That's going to be ln of 2. And now my right-sided limit at 2 is going to use this second rule here. That'll be 2 squared times ln of 2, or 4 ln of 2. Comparing these two things, ln of 2 and 4 ln of 2 are not the same number. Since my left and my right limits do not match, that means my overall limit as x approaches 2 is not defined, does not exist, so that would be answer choice E. For this problem, we're trying to find the limit as x approaches 5 for this piecewise function. Now, since 5 is a border value, that means we have to take a look at the left and the right side limits and see if those match. So let's find the left side limit first. Limit as x approaches 5 from the left. That's going to be 5 over 2. We're using this first rule here. This is the before rule for 5. And that's just 5 over 2. Can't really simplify it anymore, or you could make it 2.5. We also need to take a look at x approaching 5 from the right side. For that, we're going to be using this after rule here, the rule that applies to values of x that are greater than 5. So that's going to be 2 times 5 minus 6, or 10 minus 6, which is 4. Now, since 5 halves and 4 do not match up, that means that our two-sided limit at 5 does not exist. On this problem, we're trying to find the left side limit for this absolute value function. So in order to find this, we need to turn this into a piecewise function. Let me just let all of this stuff here equal x, just so I can refer back to it quickly. And now for my piecewise function, I need to find a border value. The border value is going to be whatever zeroes out the absolute value stuff, since we need a rule for what happens when the stuff inside absolute value is negative versus positive. So 0 is kind of the border between those. So that's going to be x equals 2. We're going to have a rule for what happens if x is less than 2, and a rule for what happens if x is greater than 2. If x is less than 2, that means the stuff inside absolute value is negative to begin with, so we have to multiply it by negative 1 to make it positive. So I'm going to rewrite this rule as 2x minus 4 over negative parentheses x minus 2. And down here now, when x is greater than 2, that means the stuff inside here is already coming out positive on its own, so we don't need the absolute value anymore for that rule. All right, in order to keep going on this one, I need to simplify these, because if I plug 2 in as things are, I'm just going to get 0 over 0, which is not helpful. So I can factor a 2 out of the numerator on both of these, leaving me with 2 parentheses x minus 2 in both of those numerators. And this is a nice thing, because these x minus 2's in each rule can now cancel, leaving me with negative 2 for the first rule and positive 2 for the second rule. All right, well, we wanted the left side limit at 2, so that means I have to do the before rule for x equals 2. That's going to be this first rule here that gives me a constant value of negative 2 back. So my left side limit then is just going to be that value of negative 2. For this one, we have this piecewise function, and we're trying to find the following limits here algebraically. So first we want the limit as x approaches 0. Now 0, we notice, is a border value between two of these rules, so we have to consider both the left and the right-sided limits separately. So for the left-sided limit as x approaches 0 from the left, we're going to be using this first rule. Plugging 0 into this x here, we just get 0 as that left side limit. Now for the right side limit at 0, we have to consider the second rule, the rule that covers the values that are just a little bit bigger than 0. So that's going to be 0 squared if we plug that in, which comes out to 0. Since the left and the right side limits give us the same number, therefore the two-sided limit at 0 is also going to be 0. All right, moving on to the next one. As x approaches 1, now 1 is not a border value. It's actually contained completely within this rule here, the x squared rule. So for this one, we just have to do 1 squared, which is 1. And then for part C, as x approaches 2, 2 is a border value between the second and third rules. So for the left side limit at 2, we're using the second rule here, doing 2 squared. So that's going to be 4 for that limit. And then for the right-sided rule, we have to use this next rule, 8 minus x. So we're doing 8 minus 2 in this case, which is going to give us 6, which does not equal 4. Therefore, because the left and the right-sided limits do not match up, that limit at 2 does not exist. On this problem, we're trying to find the limit as x approaches -1 for this absolute value function. So with absolute value, the way to deal with this is to split it into a piecewise function and then find the left and the right side limits at the border value. Now, in this case, let me just start by letting all of this stuff equal f of x just so I can refer back to it quickly. So splitting this into a piecewise function, let me pick my border value first. That's going to be whatever makes your absolute value expression come out to 0. So that'll be a border value of -1. So I'm going to have a rule for what happens when x is less than -1 and a rule for what happens when x is greater than -1. Now, if x is less than -1, that means that this stuff inside the absolute value is coming out negative. So absolute value is going to have to force it to come out positive, which means absolute value is going to end up multiplying whatever is in here by a -1. So I'm going to rewrite this rule as 4x plus 4 over negative parentheses x plus 1, because this just forces whatever came out negative in here to be positive, which simulates the absolute value. Next, if x is greater than -1, well, the stuff inside here is coming out positive anyway, so we don't even need the absolute value there. So there's our 2 rules for our absolute value piecewise function. Next, I'm going to simplify this a little bit, because you'll see if you just plug -1 into both of these, it's going to come out to 0 over 0, which is no good. So simplifying, I notice that I can factor a 4 out of the numerator in each of these rules. So 4 parentheses x plus 1 for each of those. And that's really cool, because that x plus 1 can cancel out with the x plus 1 in the denominator for each of these. So my top rule now is going to just end up simplifying to -4, and then this rule down here is just going to be +4. All right, time to look at the left versus the right limits. The left side limit at -1 is just going to be this constant -4. Right side limit at -1 comes out to a +4. Since negative and +4 are not the same, since the left and the right limits do not match, that means my overall limit as x approaches -1 does not exist for this problem. On this problem, we're trying to find the limit as x approaches 0 for this piecewise function. Since 0 is a border value between 2 different rules, we need to find the left and the right limits to see if those match before deciding on the two-sided limit at 0. For the left-sided limit, we're using the before rule here, governing the x values that are less than 0. So plugging 0 into all these x's, this is going to be 0 minus 0 plus 2, so that's just 2 for the left-sided limit. For the right-sided limit, we have to plug 0 into the after rule here, so 2 times the cosine of 0. Now, cosine of 0, you might remember, is 1. That's just the x value on the unit circle at the angle 0. So that's just 2 times 1, which is just 2. Since the left and the right side limits agree, since they're both 2, that means that the two-sided limit at x approaching 0 is also going to be 2. For this problem, I'm trying to find the left-sided limit for this absolute value function. To make my life a little easier, I'm going to turn this into a piecewise function. So I'm going to let all this stuff be represented by f of x, just so I don't have to keep writing it. And now my piecewise function, I'm going to need a border value. That's going to be whatever makes the stuff inside absolute value 0, because that's where you need different rules in absolute value. One for what happens when the stuff inside is negative, one for what happens when the stuff inside is positive. So the place where we change from negatives to positives is x equals 3. So I have one rule for x being less than 3, one rule for x being greater than 3. And if x is exactly 3, then this whole thing comes out to 0 over 0, which is no good anyway. All right, so for my first rule, where x is less than 3, where the stuff inside absolute value is negative, I'm going to have to force the stuff inside absolute value to come out positive. And I do that by multiplying all of this by a negative. So I'm just going to replace my absolute value with a negative parentheses, x minus 3. And now for the rule where x is greater than 3, where the stuff inside absolute value is positive, I can just drop the absolute value completely and call it a day on that. Now, in order to keep going on this problem, I need to simplify these two rules, because if I just plug in 3 with either of these rules, I still end up with 0 over 0. Now, you'll notice here these x minus 3s are a common factor that we can cancel, so my top rule ends up reducing to negative 1, and this lower rule here is just going to be positive 1. Since I'm looking for the left-sided limit at 3, I'm really only concerned with this top rule here for the values of x that are less than 3. So limit as x approaches 3 from the left is just going to be this constant negative 1, which gives us answer choice B. For this problem, we're trying to find the limit of this absolute value expression as x approaches negative 7. If we already plug in negative 7, we're going to quickly get 0 over 0, which really could be any of these things. So instead, we need to turn this into a piecewise function and evaluate the left and the right side limits. So I'm going to just let all of this stuff equal f of x so I can quickly refer to it. And now for my piecewise function, I need a border value. I'm going to use negative 7 because that zeroes out the absolute value expression. So that's kind of the border between stuff that makes the absolute value inside stuff negative versus positive. So we have a rule for x being less than negative 7 and a rule for if if x is greater than negative 7. So my first rule, when the stuff inside absolute value comes out negative in this case, I'm going to just have to negate all of this absolute value stuff. So I'm going to write x plus 7 over negative parentheses x plus 7. So this simulates the whole making negatives positive piece of absolute value. And now for the case where I have numbers that are coming out positive inside absolute value, well, I don't really need to do anything special, so I'm just going to drop the absolute value for those numbers. All right, now if we plug in negative 7, we're still ending up with 0 over 0 for both of these, so we're going to go ahead and simplify both rules now. Since I have x plus 7 over itself, I'm really just canceling these out and leaving me with negative 1 for the first rule and positive 1 for that second rule. And now, if I take the left-sided limit, that's just going to be this constant of negative 1, and the right-sided limit at negative 7, using the after rule here, that just returns a constant value of positive 1. Since negative 1 and 1 don't match, since my left and my right limits don't match, that means the two-sided limit at negative 7 is going to be not existing as well. So that means I have to pick answer choice D.